go.
Cole, I'm going to duct tape your mouth, and that's on tape, so there's proof that, like, it might happen, okay? All right. Settle, Stewie, turn. There we go. All right, so I am glad to see you guys are all awake on this Monday morning. That's a nice change. But we do need to do some work today and tomorrow. Hopefully not tomorrow, as long as you bring in money for stall days.
We will.
All right.
Not just
Keep that chatter up in your other classes as well, right? So keep it going. We ended in our notes with fission. What does fission sound like? Division. Show me with your hands what division would look like. I like it. You're showing me that atom, that big nucleus, that large isotope is splitting, right? All right. We're going to move on to our third topic of this unit and our final topic, and this one is fusion. So this is the second nuclear reaction, and this is with two nuclei with low masses, so they're small, right? And they're going to combine to form one nucleus with a larger mass. So you're taking two small, fusing them together to make one larger. Now, is it very large? No, but it's bigger than what the two small ones were, right? And we'll take a look at what's needed for that. So fusion, think about it. If you have a broken bone, it might need to fuse to come back together, right? And so that's what fusion means. It's the coming together of two things or multiple things. So fusion equals coming together. So you have two that are separate, coming together is what's happening here. And so for this to occur, you have to have these positively charged nuclei because that's where the protons are. So that's why the nucleus is positive. And that was one of your questions that you've seen. Those nuclei have to move very, very, very fast. Think of them as like slamming together. Excuse me. Uh-oh, sick. Better go home. Just kidding. And so we know that those nuclei, if they're positively charged, show me again with your hands what positive and positive would typically want to do. Right? They typically would want to move away from each other. But if we're trying to slam two positives together, we have to overcome that repulsion, or they have to overcome that repulsion. That typical repulsion, that spreading apart that they would normally want to do, we have to overcome that. And the way that happens is get those nuclei moving really, really, really fast. So basically they get moving so fast they just slam together and they kind of unite. We call movement kinetic energy, right? Last year we had a whole unit on potential energy and just barely touched on kinetic. We're going to have a whole nother unit later this year with potential and kinetic. But think of it, potential energy is that energy of position, that energy that's waiting to happen. Kinetic energy is the energy of movement. So if we talk about kinetic energy, we're just talking about more movement, okay? And so kinetic energy is related to temperature. And this is something that we're going to talk about probably in like 2 units with our states of matter. As you heat things up, those molecules start moving. And so the more they move, the more heat they have. All right. So when you rub your hands together, right, we've all felt that heat because we're having kinetic energy and our hands are rubbing back and forth. The more you rub them, the hotter they get, right? That's exactly what's happening to molecules, to particles, to atoms, to these nuclei. If you move them very, very quickly, they're getting hotter and hotter and hotter and hotter, and then they slam together and they fuse. Okay? So for fusion to happen, one of the requirements is that it has to be at extremely high temperatures. Okay? So again, we're going to have a whole unit on kinetic energy and temperature, so we'll get into the specifics more, but what you need to know for this unit is kinetic energy is movement. Think of like the hands rubbing. When things are moving, they get hot, and we need extreme hot for this fusion to take place. All right, so this process is happening naturally in our universe all the time. It's actually happening in our sun which is a star, and all other stars as well. This is what produces the energy of our sun. This fusion process. So, pretty powerful, right? Because if this fusion process is taking place all the way up in space, in our sun, and we can go step outside right now, and shockingly enough, it's a sunny day, we could feel the energy from the sun, you know, all the way down here on Earth, which isn't shocking, we know that. But think how intense that heat has to be for it to be able to travel all those millions of miles to reach us, okay? So, the core temperature of the sun is about 15 million degrees Celsius, so pretty toasty. And so, because the temperature is so hot, that means all of these atoms in the sun or in the stars are moving a lot, moving at extreme speeds. And so that temperature causes that extreme movement, and that is what is allowing this fusion to take place. What's really going on is that the hydrogen nuclei are going to fuse to create something we call helium energy. Because think about it, hydrogen has one proton, helium has two. So if you take a hydrogen and slam it with another hydrogen, you form a helium. Okay. And obviously that's a very simplistic version. But this is the energy that sustains life here on Earth, because without the sun's energy, we would not be able to exist. And so fusion is basically the energy that's keeping us alive when you come down to it. Okay, it's keeping us warm, it makes everything grow, right? Everything comes back to starting with the sun, right? So this is kind of showing, obviously we get some free neutrons that usually get released. Hydrogen form together to form a helium. And so that's basically, like, I don't need you to know like extreme specifics, just understand that a lot of times you're taking an isotope of hydrogen and you are going to use two of those to fuse together to make that helium. So as the sun ages, we're going to have less and less hydrogen because those hydrogen atoms are fusing together to form helium. So basically you're taking the hydrogen and they're combining into helium. So eventually you're going to end up with more helium than you do hydrogen. And so this is the very simple reaction that produces the energy that is in our sun and all stars. Because I'm taping these video notes, obviously for Google Classroom, for the absent people, we're going to come back to our videos at the end. So we're going to watch a video about stars and like this process and how it works. So we'll get to that at the end here. All right, so small nuclei, like our isotopes of hydrogen. Remember, deuterium and tritium, they're special names for those isotopes of hydrogen, but all they are is hydrogen, right? One proton. Deuterium has one neutron, tritium has three, because it's basically like hydrogen 3. If we add up all the protons and the neutrons for the mass number, so this is like hydrogen 3, this is like hydrogen 2. They just have a special name, deuterium and tritium. They're going to fuse together to make this helium. Now we know it's helium because it has 2 protons, all right? And so you take these 1, 2, 3 neutrons, and what happens is the helium is formed, but then it basically kicks out an extra neutron. Okay? So small nuclei are going to combine to form the new elements, and obviously this is how the majority of most elements on Earth are created, because every time we combine, all right, you guys need to stop. Every time you combine protons, you're creating a new element. So we go one proton for hydrogen, put them together, that makes 2. Well, helium has 2. So if we took a helium and a hydrogen and put them together, then they have 3, and that's how lithium was formed. So, very simplistically, obviously. But when we're talking fusion, typically this is just happening with, hydrogen forming into helium. Now, the reason that this can become very important to us, besides that fusion is what it is our basic energy source and keeping us all alive, this would also be a very, very powerful, clean way to produce electricity, to transfer that nuclear energy into electrical energy, okay? So the reason why is that it doesn't deal with anything that's radioactive. Fission is dealing with those radioactive isotopes, right? They're emitting that radiation, that deadly energy. So if we can use fusion, we can bypass all that nuclear waste and all the dangers of the fission nuclear reactions. Okay. Bad news is that think how hot the sun is. We have to have extreme temperatures to make this fusion process happen, right? It actually has to turn into something called the plasma state, which again is something that we'll talk about when we get to our states of matter. But there is a fourth state of matter called plasma, and basically it's like really high energy gas in a way. And again, we'll talk about more later. But it has to reach several million degrees Celsius for fusion to take place. That causes some problems, okay? And so they're actively working on this technology, but we don't have it quite mastered in a usable way just yet. Working on it, right? So obviously it would be great because it's clean, there's no radiation, no pollution, but to be able to get things that hot causes some problems. So we'll watch a video that's going to kind of explain this process a little bit here too. So obviously if we could master the technology, it would be an amazing source of energy, absolutely beyond our wildest dreams, really like our best case scenario if we could get this to work. The fuel's good enough to fuel our planet now, right? That's what we're living on, is the sun's energy. So if we could basically use that same that same process and have the fusion process turn that nuclear energy into electrical energy, that would be just phenomenal, right? It would solve all of our energy needs forever. Sorry, go back. And so this is the goal, and magical. That's the goal of this nuclear fusion idea. I think now we have a lot of science, like a lot more research is being done, putting like attention into fusion versus fission, just because there are so many drawbacks to having that fusion as our power source. All right, we'll get back to that one in a minute. All right, so we're going to look at weaponry as well, because fission and fusion both can be used for generating electricity and creating weapons. So we looked at that with fission, so now we have to look at the weapon component with fusion as well. So there are fusion bombs. These are known as hydrogen bombs and thermonuclear bombs. So these, even though they're dealing with atoms, they are not the atomic bombs. They're not nukes like we talked about with the fission bombs. They have their own name, hydrogen bombs and thermonuclear. And obviously they're going to involve a fusion reaction, not a fission reaction. Yes?
If they can't get a fusion reaction to happen in a power plant, then why can they get it in a bomb?
I'm going to let this video kind of explain this. Because the thing is you're not trying to, you only have to control it for so long and have things heated up. Like if you have this power plant, it's like the continual heat, you know what I mean? Like the end game for a bomb is an explosion, right? So that's part of the reason, but after you watch the explanation on the video, it might help. Okay, so what's actually happening, and the video is going to show this better than I'm going to explain, but you get the isotopes of hydrogen. Typically it's deuterium and tritium, and those are kind of like your reactants, right? We know that you have to have high temperatures. So to do that, you get the nuclei moving really, really, really quickly. Get them moving fast and that heats things up. So we have to have extremely high temperatures. And then the strong nuclear attraction can take place. Remember, that's the slamming together of the protons, and then the neutrons there can kind of help act as that atomic glue. And instead of like breaking the attraction like we do in fission, we're trying to cause that attraction, trying to overcome the natural repulsion of the two positive nuclei, slam them together, and so we can get this new helium. And so the two hydrogens have come together and it's now helium, because we know that the number of protons is like the identifier, it's the fingerprint, right? It's that permanent number. So if hydrogen and hydrogen now are together, now it's two protons. Two protons means that it is now helium. Okay? And so the new helium has less energy than the original two hydrogen isotopes did. And so that extra energy has to go somewhere, and it goes boom, basically. That is the explosion. The energy that gets released is the explosion. Okay? All right, let's back up a second. We're gonna take a look at some of these videos.